All right, welcome back to College Algebra here, and we are going to be talking about the last little section we're going to be talking about for the year, and we got plenty of time to do it, so this is excellent. But we are going to talk about exponential functions. Now, up until now, we've been studying polynomials, which looks something like like x squared, or like 3x to the fourth, or something like that. We also studied rational functions, right? 1 over x, which would be x to the minus 1, right? Because the exponents, when they're in the denominator, we use a negative number to say it's reciprocal of. So x to the negative 2 would be 1 over x squared. Okay. We also have x to the 1/2, right? And a rational thing like this, rational exponent, this means the square root of x. X to something like the 3/4 would be the 4th root of x cubed. And the thing is, it doesn't matter. Like, you could take x cubed and then do the 4th root, or you could do the 4th root and then cube it. Okay. So if I did something like 16 to the 3/4, you could either do 16 cubed and then take the 4th root of whatever that was. What is 16 cubed? It's going to be like 512 or something. 16 cubed, 490. Okay, bigger than I thought. 4096, and then we could take the fourth root of that, 4096. And then what we could do is and what you're going to do is just this. You're going to say 1/4, parentheses, 1/4. All right. And there we go. It's going to come back to 8. Okay. Or you could take 16 to the 1/4 power, which is the 4th root of 16, right? And then cube it. And the 4th root of 16, that's going to be 2. And 2 cubed is 8. So it doesn't matter which direction you do this in. Okay. Just, it's something I've noticed students have questions on later on, is they, does it matter which way you go? No, not really. So that's what rational exponents look like. Okay, so we've had the regular ones, right? Integers, which you just square, 4th, cubed, whatever it is. Those are pretty straightforward, and usually you're going to use a calculator to help you out. We have reciprocal, which are fractions. We have rationals, which are square roots or 4th roots or cube roots or whatever the fraction happens to be. But you could also raise it to a power and take a root at the same time. It means we can all sorts of things like this. And now we're going to define a function that's going to look like the base, and instead of having the x in the baseline, the x is going to be in the exponent position, and this is going to be a number. And just like over here, right? Well, not quite. B has to be bigger than 0, and it can't be 1. Okay, so it could be a fraction. That's fine. You could have like 1/3 to the x power. That's okay. You could have 3 to the x power. That's okay. All right. You can't have -2 raised to the x, though. Like, why can't you do -2? Like, well, x could be any number, right? The domain for this function is going to be, well, the x can take on any value. So x can be any number, -infinity to +infinity. Now, if you remember what x to the 1/2 means, what if I put in -2 to the 1/2? So we get the square root of -2. Now, we know we did some complex numbers, but this isn't going to work, okay? Because you're also going to have -2 to the 3/2 and to the 5/2, because x can be any value. So if I looked at the graph of this thing, there'd be a lot of holes here, okay? Now, -2 to the 1/3 is fine. You can take a cube root and you still get a real number, okay? If I take -8 to the 1/3, right? That's -2. It's the cube root of -8. Can you come up with 3 numbers that when you multiply them together, you get -8? Like, sure, it's -2, -2, and -2. right? Those multiply all that together, we get -8. So when it's, if b were allowed to be negative, you would have some values that would be graphed and then some values that wouldn't. And you would have this kind of a, as you would graph it, you'd have like, a lot of disjointed points. We really don't want to deal with all of that, okay? We don't want to say, well, b could be negative if it's defined. Like, no. So that's why it has to be positive. And if it's one of the things we're going to do later on is we're going to equate exponents. Okay, that's a very common thing that you're going to get something like 5 to the x plus 3 is equal to like 125 to the x. And you're going to say, oh, but 5 is really 3 cubes, so it's, 5 cubed to the x is equal to 5 to the x plus 3, and then you're going to get 5 to the x plus 3 is equal to 5 to the 3x. Remember, okay, I'm counting on you guys to remember all of your exponent rules like you know them like a pro. Okay, I'm kidding. We're going to cover that. But we have a to the r to the t. What happens is that we can multiply them together. Okay, that's a rule about exponents. So a to the r to the t, we multiply them together. So if I have 5 to the 3 to the x, that's going to be 5 to the 3x. That's how that happened. And then what we're going to do is we're going to equate the exponents. So we're going to say x minus 3 is equal to 3x, and then we're going to solve. Okay, and that's going to be like x to, 5 to whatever is going to be equal to 5 to the 3 whatever. Okay. If we let b equal 1, then I can do like a 1 to the 2 is equal to 1 to the 3. That's all true. But when we go to equate the exponents, what happens? And we really don't want to let this happen. Excuse me. Okay. So that's the reason for the restrictions on b. So we're going to study the class of functions f of x is equal to b to the x, and we're going to note that b has to be positive and that it can't be 1. Okay, so that's when you're reading this, right? Don't get intimidated. Like, why did they take these out? Like, don't turn off when they say that. Okay, that's the reason why. All right, so one of the things we're going to do is we're going to graph these things. Okay, and your book starts with 9 to the x. I wish they started with a much smaller number. Numbers that are closer to 1, like 3/2, are a lot easier to graph than things like 9 to the x. But so the bigger number you get, the harder, well, it's not hard to graph, but the numbers get really big really fast. So we're going to make a t-table. We're going to say x, and then we're going to say 9 to the x. And since x can be any value, right, we're going to go ahead and I'm going to say, well, what about -2, -1? I'm going to say -1/2 in this case. 0, 1/2, 1, and 2. Okay. Now we can have more numbers, but the idea is that this should give us an idea. So 9 to the 0. Well, anything except for 0 raised to the 0 is 1. Okay. 9 to the 1/2. Well, that's right. That's the square root of 9, isn't it? So that's going to be 3. So I'll put in 1 and a 3 here. 9 to the 1. Okay, that's about the nicest question I could ever ask you. And then 9 squared, that isn't too bad either, right? That's just 9 squared is 81. Okay. Now remember what the negative means, right? That is a reciprocal. So that is 9 to the -1/2. So that is 1/9 square rooted. Okay, so that's 1/3. Okay. 9 to the -1. Well, again, the negative in the exponent position needs to take the reciprocal. So we're going to say that's 1/9. Okay. And then 9 to the -2, well, that's 1/9 squared, which is 1/81. That's going to be a much smaller number than we can really graph, but I'll go ahead and do that, right? So What does 1/81 look like? Okay, 0.0123. Oh, look at that. 0.0123456789. Go figure. I wonder if that keeps going. Okay, so 0.0123. Okay, this one is 0.111, 1/3, 0.333, and all of these are easier to graph. There aren't any negative numbers on my chart, are there? Right? There won't be. Okay, there won't be any negative numbers on my chart. So when I go to graph this thing, right, all I need is quadrant 1 and 2 because I don't need any negative y's. Right? So I could type in, here's a half, here's 1, 1.5, 2. -1, oh, sorry, -0.5, -1, -1.5, and -2. Okay? So, okay, great. Now what we're going to do is we're going to see, well, what are my y values? Okay, when x was 0, y was 1. Okay. When x was a half, we were at the square root, or we were just at 3. 1, 2, 3. Okay. When we were at 1, oh, you know what? I'm going to change my scale a little bit. That's not going to work out. Okay. This is why 9 is going to be a tough number to graph for me. But let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so 0, 1. So it's much smaller. At 1/2, we're going to be at 1, 2, 3. At 1, we're going to be at 9. Okay, let me get rid of this. This isn't there. All right. At 3/2, right? What's the line with 3/2? So I should have put that in my little thing, but I didn't think about it. So we could say 9 to the. Okay, don't forget the parentheses on this, because if you leave that the parentheses, it'll say 9 to the 3, and then divide everything by 2. You don't want that. You want 9 raised to the 3/2. You get 27. That's going to be way up here on my graph. Okay, it's going to be like up here somewhere. All right. Remember 9 to the -1/2, that was 1/3. And then 1/9. And it's going to be 1/27, which is going to be down here. And -2 is going to be 1/81. So this graph looks something like that. All right. It just goes up, up, and away here. Every exponential graph has this shape. Okay. Now, the bigger the b, if b is much bigger than 1, the sharper this corner is going to be. Okay. We're going to get a really sharp corner if b is a big number. And when I mean a big number, I mean like 5. 5 is a big number. 9 is huge. 10 to the x is a very common thing to deal with, but that's almost an L, okay, or backwards L. When b is a smaller number, when b is close to 1, okay, even 2 is kind of a big number. I mean, when I say close to 1, I mean like 8/7, okay, or 3/2. Then we're going to get a much gentler bend here. It's going to look more like something like that. All right. So realize that when we pick a larger value here, like 9, it's really going to be steep over here. And we pick a smaller number, it's going to be not quite so steep. So we're gentle. All right. So yeah, that's the basic idea of an exponential function. We're gonna work a lot more with that. But just to get us started on the first problem here, okay, this is f of -3. So what they want us to do is we want 4 decimal places. So we want 9 to the -3. Okay, and most of this is going to be, I mean, there's a lot of, how many problems are there? There's 15. Okay. Most of the problems at the beginning of this sections are things like, can we get used to the idea of typing this in our calculators? Okay, so I know that a lot of this is going to be a little bit easier, But I also know this is the first time for a lot of people. Okay, so parentheses, and we have to hit negative. We have to hit this negative. Okay, this one, that's minus sign. It's not a negative sign. It'll say error because you didn't give it 2 arguments. Okay, whereas the negative, it's okay to have 1 argument. Okay, but we said 4 decimal places, so 0.001, we'll call that 4. So 0.0014. Okay, we're just testing out the calculator kind of a thing at this point. That's all we're doing. That's all they want you to deal with. Okay, f of 5.3. Like, what the heck does that mean? Well, that means it's it's a weird number, but that's allowed. Okay, so 9 to the. In this case, you don't really need a decimal or a parentheses because this is all put together. All right, there we go. That looks delightful. Okay, so what is that? 114. Oh, good Lord. Let me go ahead and do this because I'm not going to remember that number. So this was 114,152.466. I'm going to guess 7. I'll bet that's what's going to happen there. Oops. I wanted to test this guy out. All right, it's pretty happy. F of the square root of 10. So this is 9 raised to, right? And I am going to use parentheses here. I don't think we have to, but you never know. And I would rather be more safe than sorry about that. Okay. Okay, that looks great. 104. Oops. There we go. 1041.3094. Okay. So great. And then the last one, f of pi, like I said, it doesn't matter what the x happens to be. Okay, so f of second function, pi. Okay, 995.04. 0416. All right. Fantastic. So that's the idea of these things. They're going to have us do 1 over 9. Okay, so let me show you something that's really kind of neat with all of this. By the way, all of the stuff that you learned in chapter 1 about the function transformations and the graph transformations, all of that applies. So we're going to learn how that works. So you're going to get a little review of graph transformations as well. But we can have 1/9 raised to the x power. Okay, so let me show you something really neat about 1/9, right? 1/9 is really is really 9 to the negative 1 to the x. And we just talked about like what's a to the s to the t, and that is a to the st. Now most of the time, when you first learn it, they have you do the problems this way. But in reality, most of the time you use this, you're going to use it in this direction. You're going to take 1 over 9 to, when I say, well, we can write 9 is 1 over 9 to the x. And in this case, I am going to do it in this direction. But this is 9 to the negative x. Do you remember what happens when there's a negative on the inside of the function? Like, do you remember what the difference is between, say, we have our parent function, and I put the negative on the outside, what happens? Or if I put the negative on the inside, what happens? If you put the negative on the inside, remember that, here's my, I can use colors. Okay, I can say, well, here's my parent function. Right, this is the square root of x. And here is negative square root of x, right? It flips it vertically if it's on the outside, but if it's on the inside, it flips it horizontally. Okay, so we would have something like this. This would be the square root of negative x. Okay, the same things are going to happen when we deal with this exponential function. All right, so we have 9 to the x, right? It looks something like this. I'll do it in the same idea here. What's 9 to the negative x going to look like? Or 1/9 to the x. it's going to flip this across. So instead of going bigger and bigger and bigger here, it's going to get smaller. And then this side is going to do something like that. It's just going to flip it. Okay. So that's what we're coming up against. Okay, is what happens when we get that. And quite honestly, that's a very common function too. Okay, that's almost a class unto itself of b to the negative x, which is 1 over b to the x. This function looks something like that. Now, I'm not saying you have to memorize this one, but before too long you probably will, just because this is usually associated with decay functions. So if you're looking at like radioactive decay or declining population, you usually get a curve like this. If you're talking about, you know, a growth function, right? You're talking about, you know, mosquitoes are notorious for growing out of control. We're going to get a function that looks something like that. Okay, the b to the x. Okay. All right. So let's see here. I think this one's the same idea. They're going to tell us to do this again. So g of -2, right? We're just going to say, well, this is parentheses 1 over 9 raised 2, and we're going to write a -2 here. And we should expect, right, the reciprocal, which is going to be 9, and then square it. We should expect 81 here. Okay, thankfully, they decided to give numbers that we could figure out in our heads a little bit. Okay. See this one, there's no way, right? So 1 divided by 9, oops. Okay, and the parentheses really are important in this case because exponents happen before exponent, or yeah, exponents happen before division. Okay, so even though actually it is what you want to do, I would be very careful about doing parentheses with exponents. Okay, what was this? What did they want this to use? 4 decimal places again? 4 decimal places. 0.007, 0.0080. I'll put that leading 0 in there because they get mad at me if I don't. All right. Square root of 2. Why didn't they do a half? Okay, 1 divided by 9. Parentheses. Square root. Okay, and that should give us that one. Okay, so 0.0447. All right. Oh, we're not ready for that yet. All right, I'm gonna keep going. We'll get to the story behind this one, but we're not ready for that one just yet. All right, so we'll come back to that one. Which of the following exponential functions? B could be anything as long as it's positive, so not this one. And it can't be 1. So this is fine. This one is not. This one's fine. This one isn't because the exponential, right? The variable has to be in the exponent position. And again, the variable has to be in the exponent position. So this one is not. This one is not. This one is. This one is not because it's negative. This one is because we don't care what the base is as long as it's positive. All right. All right. We kind of did one like this. We started. All right. See this one's okay. We'll come back to that one. Okay. Graph transformations. All right. What was like if you just tacked on, right? If I did like x, I'll go back to blue. If I just had like an x squared, right, and I subtracted like 4 from it, okay, what did the 4 do? Well, here's our parent function. Right, here's our parent function, was x squared. And then this 4 moved it down 4 spaces, didn't it? 4, and it just moved it down by 4 spaces. That's all that happens. Okay, so all of those rules that we learned before, and I will go over them when they happen. Okay, so we're going to investigate those because I know that you all have perfect recall about what happened 2 months ago, and you're able to do that. Okay, so we're going to use transformations of the graph. So here's our graph. Okay, domain and the range. Did we let that happen? Oh, okay. For this one, all we have to do is move this thing down by 4 points. I don't want to. Okay, so we have 0, 1. We're just going to say 1, 2, 3, 4. Okay, done. Okay. Again, you'll notice when we first started that one, okay, it again didn't have any negative parts. So what that means for us is that we have a horizontal asymptote. Okay, we have a horizontal asymptote at y equals 0 in this case. All right, so every exponential function has horizontal asymptote. Unless you transform it, move it up or down, we're going to have y equals 0 as a horizontal asymptote. These do not have vertical asymptotes, so no vertical asymptotes. All right, so there we go with that. So when they ask, like, oh, what's the domain and range? Okay, we can do that. The domain, that's everything, right? Negative infinity to positive infinity. Now the range, I like it when they give you the graph to deal with it, okay? Because we can see what's the lowest point on this graph. Well, it's not quite -4, okay? So we're going to do a thing like not quite, okay, -4. But you can tell by the graph, right? The sky's the limit. So that's going to be as much as you want, right? And then an equation for the asymptote is going to be y equals, well, again, we moved the function down 4 spaces. Normally I would say y equals 0, but if we move everything down 4 spaces, we have y equals -4. All right. All right. Now, do we remember, okay, what happened when we had when we had like an f of, say, x minus h, right? It moved it horizontally, and x minus h was, it moved to the right h units. If positive, then we move it to the left, okay? So if I do something like, if we had, I would do square root. I had, see, x plus 4. Well, when's the square root going to be 0? So when x is -4. So even though normally the parent function started here, right? This is y equals square root of x. We're going to move backwards, right? We're going to move backwards 4 points, or move to the left. Okay, 4 points. So again, we'll go ahead and I'll use that one. Okay, 1, 2, 3, 4. So we have a horizontal shift, right, of 4 to the left. So here I have 5 raised to the x plus 3. Okay, so we have f of x is equal to 5 to the x plus 3. So my horizontal asymptote isn't changing. Okay, but this is going to be, I'm going to move this graph, right? I'm going to move this 3 to the left. Okay. Also, you can think about this because with different stretches in the polynomials, it really didn't matter which way you did it. Okay, if you factored it out of the equation, you could say it's a vertical stretch or compression. But if you put it inside the parentheses, right, it could be like this way, right? If I did the square root of 4x, technically this is a horizontal compression, right? But I could also say that this was the square root of 4 times the square root of x, which is equal to 2 root x. So now it's a vertical stretch. By the way, with all of these little transformations we have, this is a way to make it go faster, and this is supposed to be a tool to help you. If this is not helping, you could always reinforce your thought. You can like make a prediction and then reinforce that thought by making a little t-table and checking out what the graph looks like for yourself. Okay, so all of this is supposed to make your life easier, but if it isn't, I would recommend like do the t-table and then compare a guess that you make to the t-table and see how well you're going to do with that. Okay, so this is, again, it's to reinforce your intuition. And there are certain transformations, like I won't try to untangle it. I'm just gonna do this, okay, and not worry about it because there's too many to track. Okay, so this is also, right, remember this is 5 to the x times 5 to the 3. There's a rule for exponents, right? A to the r times a to the s. If the bases are the same, we can add the exponents. Okay, so this is 5 to the x times 5 to the 3. Well, what's 5 to the 3? It's 125 times 5 to the x. Can we combine these? Not without numbers, okay? You can't go off and say, well, 125 times 5 is 625 to the x. Like, those are way different functions, okay? That's not happening. So why can't you do that? It's because exponents happen before multiplication. So it's going to do this, and then we're going to take care of the 125. You can't go ahead and do this, right? You can't go ahead and say that's 625 raised to the x. That's not the same, all right? So when we have our 5 to the x, or 5 to the x plus 3 rather, okay, we'll go back to the thing because they'll graph it nicely for us. Okay, here's our 5 to the x. Okay, and what we're going to do is we're going to just take this thing, and again, I'm looking at this point here, right, the 0, 1 point, because that's the easiest point to kind of figure out. Then I'm just going to go ahead and take this and say, well, that's 1, 2, 3, because I'm moving it 3 to the left based off of this transformation. Okay, and now, oh, check, all right. Domain, again, the domain for exponential functions is really nice. Negative infinity, positive infinity. The range, again, we should probably check the graph, but unless you've got a vertical transformation, it's it has to be bigger than 0. That's really about it. 0 to infinity. All right. Great equation for the asymptote. We didn't move it up or down. The asymptote is still y equals 0. All right. You can't be halfway through this already. It's nuts. Okay. We have both, right? We have both a horizontal shift and a vertical shift on this one. Okay. We have a shift up by 2. We have a shift to the left, again, by 2. Okay. So here we have, and I remember there was like a way you're supposed to do this. They suggested it, but I don't remember. Transformations to graph a given function. So we're going to move up by 2. So here's 1, 2. Okay. And then we're going to move over to the left by 2. Here's 1, 2. Okay. And you could have done it either way. Right. And again, that 0, 1 point, that's the easiest to kind of mess around with. Okay. Did I have anything else? I did not. All right. Function, domain. Again, it's all real numbers. I know it doesn't look like that. Like, doesn't it stop here? I'm like, no, it just keeps going. It's just off the chart. So we don't have to worry about that. Domain of the function is negative infinity to positive infinity. And then the range, well, it's not getting any lower than 2. All right. So we have 2 off to infinity there. All right. Equation for the asymptote, again, we didn't quite get the 2, but we're close. So we're just going to go down here and say y equals 2. Okay. Normally we'd have y equals 0, but because we did a horizontal, we did a vertical shift, we've also shifted the asymptote. Okay. So let's see here. Let's look at 9. All right, now we start getting to some flips, okay? So remember, 4 to the negative x, right? 4 to the negative x, that's also the same as 4 to the negative 1 to the x, okay? So that's 1/4 raised to the x as well. So if they present it to you this way and they're trying to trick you, you're like, no, I know this one, you're not tricking me, all right? But remember that the negative inside of the x on the x there, that was a horizontal flip, right? If you had a function like that, it flipped it over here for the f of negative x. And the same thing is going to happen. It's a flip left and right. Okay? So we're going to flip it that way. Okay? There's so much I wish I would have. Okay, domain and a range. Well, that didn't actually change anything for the domain. It's still negative infinity. Oops, I don't have to write that. I do this way. Positive infinity. And in a range, look at the graph, right? Well, it doesn't quite get to 0. If I put a big number in there, right, 4 to the negative 100, I don't know if the calculator is going to take that, but it's not going to be negative. It's still going to be very, very, very small positive number. So the range is 0 off to infinity. Okay, it's all of it. Okay. Value of the asymptote. Well, we didn't do a horizontal. We didn't do a. I cannot say vertical shift tonight. We didn't do a vertical shift, so the horizontal asymptote is where it began. Okay, it's still y equals 0. All right. All right. No, I don't want to do that to you yet. All right. I will. I don't know if I'm going to. Yeah, I think I can get all the way through it. Okay, so today is a day you're going to learn a new number. Okay. And it's an exciting day because I don't think you've learned a new number since you stopped watching Sesame Street. No, I won't get all the way through it today. We'll do a new number tomorrow. Here is how credit cards screw us over. Okay. So the way we do, you compounded interest, right? That's what credit cards use, is compound interest. They compound it every month, and we pay them every month. But the compounding is that you get interest, or you accrue interest, and then next month you pay interest on your interest, etc. Okay. Banks work that way too, but the bank savings rate is so pathetically small that it's insulting rather than a force that's going to help you make money. But the formula we use for this, right, is the amount is equal to the principal